Hi everyone. In this video, what I would just like to go over is how to take a sound wave, as you see on the board, the compressions, and turn it into a graph that is useful, what we call a pressure versus time graph. So I'm going to review pressure versus time graphs, and then I'm going to show you a little something on how to get started with your lab. So let's begin by talking about how we take a sound wave, which is just represented here on the screen by these little dots, which represent air particles or air molecules compressed together. So this is a compression, and the rarefaction is in between the two compressions. So compression, rarefaction. Sound is a longitudinal wave, so it's made of many compressions. And what we want to do is we want to put this into a form that's a little bit more useful for analyzing things like frequency and wavelength. So this is a pressure versus time graph, and all I'm going to do is plot, and I'm just doing a general case, the air pressure as a function of time. And a compression has a very high air pressure, and a rarefaction has a very low air pressure. So you can see if I come down from this compression, I'll plot a high pressure and a low pressure, high pressure, low pressure, high pressure. And if I connect these points using a wave, I can get what looks like a transverse wave. And it's an easy way to help visualize a sound wave. Now, a sound wave is a longitudinal wave. It's not a transverse wave, but we can make it look like a transverse wave if we use a pressure versus time graph. And these peaks represent the compressions, and these troughs represent the rarefaction. So this is high pressure and low pressure. What I'd like to do now is just show you some examples of how these pressure versus time graphs can look different from one another. This first example, I'm going to use the left side of the screen, and I'm just going to plot two different sound waves, one of a different frequency. So here you can see I'm plotting along, and I'm drawing this wave. And again, these little dots just represent little packets of air. Those are compressions, and in between them are rarefactions. If I go to a higher frequency sound wave, what the graph is going to look like is just the peaks are going to be more frequent, which means that we have a more frequent sound wave, we have a higher pitch. I kind of messed up there a little bit. But this would be the high pitch, and this would be the low pitch on top. If we were interested in amplitude, again, I'll plot this first one here. I'm just doing the peaks. That was actually kind of bad. I'm going to try to redo that. My eraser tool. Let's see if I can do this. Compression, rarefaction, compression, compression. A little bit better. Now, if you look at this bottom graph, the compressions are the same distance apart. They're the same spacing, which means it's the same frequency, same pitch. But they're a lot darker, which means there's a lot more air packed in, so it's a higher pressure area. So I'm going to plot those high pressure points as higher and the low pressure points as lower. And you'll see a wave that has a larger amplitude, and the amplitude corresponds to the volume. So if I ask the question of these four graphs, which one is the loudest or has the highest volume, it would be this lower right-hand graph. And if I said which one has the highest pitch or highest frequency, it would be the lower left graph. What I'd like to do now is just show you how we're going to actually collect data and make these graphs in the lab that we're going to do. So I'm going to head over to a lab station and show you how to collect data using a microphone to look at a pressure versus time graph in the lab setting. So come on over to the lab with me and we'll take a look. Alright, thanks for coming to the lab, which happens to be the exact same location as the class in the video. But I just wanted to show you what you should be doing in the lab to measure the frequency of the object that you're playing the note with. The first part of the lab, you're measuring the frequency of a tuning fork. A tuning fork just plays a singular note. This is what a tuning fork looks like. And what you should be doing in the lab is when you want to play the note, you should strike the tuning fork on something soft. We have these little rubber mallets, so you'll just tap it. And the sound that you really hear, you need to put it right up next to your ear to hear the hum of the tuning fork. This is playing a 480 hertz pitch, and it makes a nice sound wave. And to measure this, we're going to be using the microphones, which just are They just look like cylinders, and the microphone part is at the end. The microphone just measures air pressure. It measures differences in air pressure. And on the screen right now, you can see the setup, and there's a green collect button. The key to the entire lab, and the thing that I want to get across in the video, is that if you hit collect, then strike the tuning fork and hold it up to your microphone, the experiment's already over. It can only sample for a very small fraction of time. We're talking, I think it's about 0.05 seconds. Yeah, 0.05 seconds if you look on the graph. So what you need to do is you need to strike the tuning fork, hold it up to the microphone, then hit collect. So you strike the tuning fork, hold it about an inch away from the microphone with the flat side, an inch away from the microphone, and then hit collect. So I'll demonstrate that quickly. I have to put the microphone on the table to do this, but strike the tuning fork, hold it next to the microphone, then hit collect. And we get a nice little sound wave there. And then if I hit the auto scale button, which is A, you can see it's a little rough, but overall I can calculate the frequency of this sound wave by looking at this graph. And that's the goal of your lab. So just to recap again, strike the tuning fork on something soft, strike it and hold it next to the microphone, and then hit collect. And that will allow you to measure the frequency of your musical object.